Alright guys, here's your Unit 14 review video, which is the last unit review video of the entire year. It's a lot of talking, which has always put me off from making this video, but I am here making it for you this year. So I have some things highlighted. I actually will briefly go through these examples as well. I'll do 5, 6, 7, 9, and 10. I might not even write out explanations. I may just vocalize them to you. 12, you got some random digit tables. 13, we'll talk about sample size and spread. 15, margin of error, standard deviation from some information. 17, flipping a coin. 22, simulations. And 24, we'll do a difference of means problem. And 26, another question about do you agree or disagree with your person based on a simulation. And lastly, 28, another coin flipping one, but from a different perspective. So coming up to the top, just so that we're aware of this, anytime we're talking about pulling a sample from a population, the population is the large amount of people, and then the sample is a portion that you're pulling out. So this would be your sample, this would be your population. So you pull out a population, or pull a sample out of a population, and you use the sample to make inferences about the population. Okay. In order to get the sample, we do what's called random selection. So that could be random digit tables, flipping a coin, random number generators, etc. And that always has to happen in observational studies and surveys for that matter, because we want to avoid any sort of misrepresentation of data, any sort of bias. And then in an experiment, your pool of people that you are doing your experiment from, you may or may not have randomly selected them to start. But then from there, you have to randomly assign them into two groups to, again, try to spread out the different variables between people and avoid any sort of bias. Okay? A blank is a summary number that describes a population. That is a parameter. Okay? P associates with P. Your parameter symbols are P for population proportion, so it's the true proportion in a population of something that happens, and mu, the true population mean. A statistic is a summary number that describes a sample. So a p hat is a proportion of a sample, or a sample proportion. An x bar is a sample mean. Now, we use these different symbols depending upon the data we're looking at. So in quantitative data, we use an x bar, which is again a sample mean, to describe a mu, which is a population mean. Okay, so sample used to describe the population. We use a p hat with categorical data. So for example, the proportion of heads that you get when you flip a coin. This is a sample proportion, and we use it to describe P, the true population proportion. Okay. Quickly looking through, if we have 32 adults selected at random and they asked who they were to vote for in November, the fact that I'm asking them and selecting them at random tells me it's a survey. I'm asking and getting answers. 20 students were randomly assigned to take a paper test. Another 20 were randomly assigned to take an online test. The mean score of the two groups was compared. This is an experiment because you are randomly assigning the students into two different groups for comparison. One is the paper and one is the test, or online test. Wait, was it? Online test, yeah. One was the paper test and one was the online test. So those are the two different treatment groups. I suppose you could say the paper is like your control. A doctor randomly selected 5 patients and took their blood pressure. He found the mean systolic blood pressure for the sample was 132 milligrams. This is an observational study. He randomly selected his patient and he measured their blood pressure. And lastly, 13 shoppers bought more expensive brand of laundry detergent. Another 13 bought the discount brand. When they sent back their opinions on detergent effectiveness, it was concluded that the discount brand was far more effective at cleaning white clothing than clothing items. This sounds like an experiment, but it's really just a survey. You didn't randomly assign people to try 2 different types of detergent and get their input. You had your people really just self-select themselves to fill out the surveys and turn them back in. Okay, so this was more of a self-selecting survey where the people who chose the discount brand weren't assigned to it, they chose it themselves. And then furthermore, they chose to include their opinions on it. All right, 32 adults in New York are selected at random and asked who they will vote for in the November senatorial election. 42% of them report that they will vote the Democratic candidate. The 95% reasonable interval for the study is calculated to be 0.38 to 0.46. Okay, now your sample size, that's how many people you took to make an inference about the population at large. So your sample size was your 32 adults in New York. So the variable there is a p-hat, whoopsies, is a p-hat because it's not how many people are voting so much as it's what's proportion of people are voting a certain way. Success versus failure. You're either voting for the Democratic candidate or you're not. So your p-hat is 0.42. Okay, the reasonable interval that they came up with was given to you. So if I want to calculate the margin of error, it's always your highest reasonable minus your lowest reasonable divided by 2, or high minus low divided by 2. So I'll do 0.46 minus 0.38 divided by 2. Okay, so I'm getting 0.04. Okay, the standard deviation is always half of the margin of error, so that would be 0.02. And this is an observational, or excuse me, this is a survey because we're asking people and getting their answers. The population that we're trying to get information about is all adults in New York State because your 32 adults in New York State were who you selected. Okay, so again, it's not the 32 adults, that's your sample. The population is the larger pool that you're picking the 32 from, which is who you want information about. So adults in New York State. Okay. What this number means is it's reasonable to say that the true proportion of people in New York State, or adults in New York State, who will vote for the Democratic candidate could be anywhere between 38% and 46%. Okay, so if I were to literally ask every single person, every single adult in New York State, who are you voting for? I wouldn't be shocked if the proportion is in between these values based on my sampling techniques. Okay, so what I've done is I've used a sample to come up with a reasonable interval of what the true proportion of the population could likely be. Okay, what is the purpose of random assignment in an experiment? It's, again, just to make sure we get a sprinkling of all the different variables between our 2 different groups. We want to avoid any sort of bias or misrepresentation that may happen by getting too many of the same type of people, I guess we'll say, into one group. So, for example, if you think about our notes where we had the elderly drivers and the adult drivers, we didn't want all the elderly drivers in one group because we're measuring reaction time. That would skew our data and cause some misrepresentation, which may show that their reaction time is slower, and it may seem like, what were we doing there? It may seem like lack of sleep is causing the slowing of the reaction time, when really it was just the age of the people. So by employing random assignment, we do the best we can to think that we would get between our 2 or 3 groups all ages, all genders, and any other sort of factors that may come into play, divided among our groups evenly, or as evenly as possibly can be. Okay. Instead of actually flipping a coin, I use an online applet to quickly see what happens when I flip a fair coin 30 times, and I perform this over and over again. This is called a simulation. And that's what I've done for you guys in class with that Rossmann Chance applet. So I'll actually show you that real quick. Okay, so just to remind you, this is the applet that I showed you in class. It's an example of a simulator. I'm going to simulate flipping a fair coin 30 times like the problem said. So I'll hit draw samples. You can see the 30 coins flipping here, and it's sorting it into heads versus tails. So we're going to end up having 18 heads and 12 tails, which makes up our 30 total flips in our one trial, and it comes out to about 0.6 here. Okay, so that's 18 out of 30. So 0.6 is our one p-hat. I had that many, or that was my proportion of heads in that trial. Okay, and I could do it again. I'm going to come up with another sample. And again, and again, and again. As long as this catches up with me. I wanted to do 7. It's going to take a minute here. But every time it finishes, it will do another plot here. Oh, there we go. It caught up. Okay. So I could do this even quicker by changing this number. So let's say like 200 more samples. There you go. And there's what's called my distribution of sample proportions, because every single one of these little dots is a p-hat. It's a proportion of heads that happened in 30 flips of the coin. If I turn on my summary stats here, you'll see that the mean or center of my distribution is about 0.5, which is where I'd expect, and my standard deviation is 0.092. Okay, so that's your typical distance on either side. That would capture 68% of your data. Okay, 2 standard deviations outside should theoretically capture 95% of your data. Okay, now if I were to reset this and change my sample size from 30 to say 100, so now you're flipping 100 per trial 200 times. Remember our standard deviation was about 0.09 something, now it's 0.048. So by increasing my sample size, my standard deviation and therefore spread and sampling variability decrease. You see this data pushing in. It's getting tighter and tighter around the true center of that distribution. Okay, and we're back. When a randomization distribution is created, some of the values may be exactly at the true proportion mean, some to the left, some to the right. This is just called sampling variability. This happens. It's like when you guys randomly selected your 200, randomly selected your 10 baseball players from our population of 200. Not every single one of you got the same baseball players. So that's called sampling variability. Which of the following is not a consideration in observational studies? Placebo. Placebo is used in experimentation. It's like a fake treatment that you give to somebody. So it makes them think they're receiving the treatment, but really they're getting something like a sugar pill. Okay, bias is something we create, or is something we consider. So, for example, if I want opinions of students at Williamsville East on the parking lot at East, like assigned parking, I'm not going to ask the freshmen in the building because they don't even drive. Another idea is if I want opinions on homecoming activities and I want to ask all of Williamsville East, that means I want my sample to represent all of Williamsville East. If I pick just my 9th period Algebra 2 class, I'm really only getting the opinions of a handful of sophomores and juniors, which may not have the same opinions that, say, a senior or a freshman would in the building, or ones that maybe aren't even in Algebra 2. So the idea is when you're doing your random sampling is you want to eliminate those scenarios, so eliminate any bias, so that sample is a true representation of the population you're trying to get information about. Chance variation is something that just happens when you randomly sample. Okay? The difference between a placebo and a control, the placebo gets something, but they think that they're getting the real treatment, so they're getting a fake treatment, and they're unaware of it. A control group gets nothing, and they're aware that they're getting nothing. Either way, they're used as groups in an experiment to help make a comparison to a treatment group. Okay, we talked about how to use a random digit table to randomly select people. So important things to note is you need to start on the line that it wants you to. So in this case, it wants me to start at line 103. It says we have We're going to select 12 cartons, and each carton has been labeled with a 3-digit code, and the codes go between 000 and 1699. Okay? In order to do this, you want to just mark off, we'll zoom in here, every 3 digits, ignoring the spaces, to help you come up with the random digits that come up. Now, let me see, what were the digits again? 000 to 699. So this 554 would count as a number that's in my interval. 679 would count. 170 would count. But as soon as I get to 977, that's outside of the interval. That does not correspond to a carton from my population, so I would skip that. Okay? 558 would fit in my interval, so that's selected. Now, if I happen to get 170 again, I would ignore it because I can't select the same carton twice. Okay, I won't finish that. Leave that for you guys, but that's the idea. Oh, also, if you get to the end of a row, you just continue on the next row. All right, so given the distribution of sample means at the right, both are created from samples of the same population. No matter which one you look at, the center is still the same. Just like in that simulation I just showed you, the center is still about the same at 0.5. In this case, it's still the same at 20. Which graph is the means of sample size 10 and which one's 50? Remember, as sample size increases, standard deviation and spread decrease. So your data goes like this. So therefore, the larger sample size must be the one with the least spread of data. The more spread data means it must have a sample size that is smaller. Okay? All right, calculate each of the following and the middle 95% for each of the following. So I give you a sample mean of 64.5 and a standard deviation of 3.1. If I want the margin of error, that's just 2 times the standard deviation. So I do 2 times 3.1, which is 6.2. In order to calculate the interval, I go from my sample, which is 64.5, and I'll add or subtract 2 times the standard deviation, which I actually already calculated, which is 6.2. So whatever that interval ends up being, I guess I'll figure it out. So 64.5 minus 6.2, 58.3. And 70.7. Okay, so this would be my reasonable interval I would use to predict the true population mean. So I used my sample mean to come up with an interval of where my true population mean could be. Coming down to this one, just because it's a little bit different, I give you the margin of error, which means in order to find the standard deviation, you need to take that and divide by 2. Notice how it goes the other way. So again, standard deviation is margin of error divided by 2. Then from the interval, I do the mean plus or minus the margin of error. Okay, and at this point, just math. You guys can figure that out. All right, Melissa has a coin. She does not know if it is a fair coin. She flipped the coin 50 times and obtained 35 heads. So right there I'm thinking, all right, there's my p-hat. That's my sample proportion. She got 35 heads out of 50, which is the same thing as 0.7. She ran a computer simulation of 100 samples of 50 fair coin flips. So notice that that means that she centered this simulation assuming the coin was fair. So assuming the mean is about 0.5, okay? She ran 100 samples of those 50 coin flips to match the 50 tosses that she threw herself. So the sample size is the same. The output of the proportion of heads is shown. So here's her sample distribution. There's 100 dots. Every one of these dots is a p-hat, which is the proportion of heads in 50 fair coin flips. Given the results of her coin flips and of her computer simulation, which statement is most accurate? Well, first of all, this is her p-hat, right? 0.7. if you look at the distribution, it's not even happening. So what that tells me, without even looking at these choices, is by random chance alone, for that 0.7 to come up on the distribution, it's extremely rare. It's not even happening at all out of 100 dots. 0% of the time in the randomizations, 0.7 came up. So for her, in one trial of 50 flips to get 0.7 is highly unusual. So I can tell you right now, her coin is not fair. Okay, I don't even need to look at the other options. Other options are just there to confuse you. 35 of the computer's next 50 flips will be heads. I don't know that. 25 of her next 50 flips will be heads. Again, that's theoretical. I don't know that. Her coin is fair. Her coin is not fair. Okay, these are out. It's really between these two. And it's because 0.7 doesn't even show up on a true distribution of our sample proportions. Now, another way you could do this is take the mean and add or subtract 2 times the standard deviation, because why not? They gave it to you. Okay, so I do 0.502 minus 2 times our standard deviation, so 0.35, and do the same thing but add it. Whoopsies. .654. Okay, so even if I calculated with an interval, I'm seeing 0.7 does not fit in that interval. It's in the outside, which means it's unusual. Okay, this is our usual expected. Out here's our unusual. So again, that means the coin must be unfair. Circular spinner is divided into 5 sectors of different colors. A student spun the arrow on the spinner 200 times and recorded that the arrow stopped in the orange sector 38 times out of 200 spins. So right there again, I'm thinking p-hat. 38 out of 200 spins were orange. Oh, I'm sorry. Yeah, 38. I think I said 28. 38. To test whether the spinner was fair, the student used a computer to simulate the number of times an arrow stops on orange in 200 spins of a fair spinner, equally divided into 5 sectors of different colors. The results of 1,000 trials of the simulation are shown below. So again, we're assuming that the sectors are all equally spaced. Based on the results of the simulation, is there statistical evidence that the spinner is not fair? Okay, so first of all, we got 38, right? So 38, this is 35, 36, 37, 38. This is 38. And this whole bar is 38. So 38 or more extreme happens a lot on a fair spinner, is what I'm already thinking. Okay? This happens almost 50% of the time, it looks like. I mean, I could count up all these bars, which would be a lot of work, but I'm seeing that 38 itself happens a lot, and 38 or more extreme happens a lot. So I don't think this is going to be an unfair spinner. Based on our simulation here. So based on the spinner, is it not fair? Yes, because 38 was the most frequent outcome. Okay, well that doesn't necessarily tell me anything. Yes, it did happen the most often, but a lot of other situations happen pretty often as well, and that has nothing to do with fair versus unfair. That's out. 8% of the outcomes were 38. Again, that really tells me nothing about usual versus unusual. No, because the distribution is approximately normal. Okay, great. Shape tells me nothing about usual versus unusual. No, because the outcome of 38 or less is not unusual, which, be careful of that double negative. 38 or less is usual. It was what that's saying. If you got 38 and you looked at it or more extreme, would it surprise you? No, it's a usual event. That's what that's saying. So that's why we can say our spinner is not fair. This is a really tricky question. Is there statistical evidence the spinner is not fair? No, I can't prove that it's not fair. It's all these double negatives is confusing. All right, Adam designed an experiment to determine the effect of Tim Hortons coffee on teacher energy at Williamsville East High School. 20 teachers volunteered to be a part of the study. Each teacher was randomly assigned into 2 groups. Group A drank 1 medium coffee. Group B drank nothing. Yikes, we're harsh here. The members of each group were asked 1 hour later to do jumping jacks for 30 seconds. Adam recorded the number of jumping jacks for each teacher and found the average for each group. He found that the jumping jacks for group A, which was the coffee, was 20.9 jumping jacks. And for group B, which was no coffee, was 17.7 jumping jacks. So right now you're observing a difference between the means, or the difference between the two groups. But you're just not sure if that difference is significant enough. Okay? So keep in mind that every teacher right now has a number of jumping jacks. So every single person in the green group, the coffee group, had a number of jumping jacks. We added up all 10, divided by 10, and we came up with an average. Everybody in the no coffee group had a number of jumping jacks. We added them up, divided by 10, got their average. Using these results, Adam randomly mixes the 20 teacher results. Okay, so now everybody's back in the pool. And then splits them into two groups of 10. So now it's not necessarily coffee drinkers with coffee drinkers and non with non. Okay, everybody's back in the pool. And then he simulates the difference of the mean 232 times. Okay? So here's your graph below. So here's your simulated differences. These are all differences, like a difference of -1 would be this bar, or more extreme. Okay? Calculate the mean difference between the groups. So A minus B. What does that mean in the context of the problem? Okay, well A was 20.9. B was 17.7. Okay, so I got 3.2. So what that means is, on average, Group A is doing 3.2 more jumping jacks than Group B. Okay, I'm not going to write that out. You can look it up on the answer key, but that's really what it means. On average, Group A is doing 3.2 more jumping jacks than Group B. Adam decided that the difference in mean jumping jacks is an unusual occurrence. Support his decision using results of the simulation. Explain your reasoning. Okay, so if I come here, zoom in, 3.2 would be right in here. There's nothing there, but 3.2 or more extreme is that bar right there. Okay, according to my scale, that counts as a 1. Ooh, hold on a second. There we go. Jeez. Lost my grid for a second here. There we go. So that's a 1 out of how many simulations again? 232. So this only occurred 1 out of 232 times in the simulation. Which is 0.4%. Okay? Do you agree with Adam, essentially? Yeah, I agree with Adam. This is an extremely unusual event. If you look at even just visually speaking, it's way at the tail end over here. It's not like in the middle, okay? So what that tells me is this experimental difference that I have observed of 3.2 is something that isn't likely to come about just by random chance alone. So the fact that I'm observing that difference, and that difference occurs 0.4% of the time, tells me that, yeah, this is an unusual occurrence, because this is occurring less than 5% of the time. So this is unusual. Okay, if you want a more eloquent way of writing your explanation, you can check out the answer key online, but just verbalizing it for you guys, that's what I'm thinking about. And that's what I'm saying. Okay, this is occurring less than 5% of the time, so yes, it is unusual. Alright, your friend insists that he has an 80% success rate for free throw shooting in basketball. Curious, you decide to attend one of his games. Of the 10 free throws shots he took, he made 4. To test this claim, you ran a simulation of 10 free throw shots with a success rate of 80%. So keep in mind, you based this simulation off of the assumption that he gets 80% of all his free throws. Okay? Based on the results of the simulation, do you think he actually has an 80% free throw rate? So basically, do you doubt him? Do you think he lied to you? So he did this simulation 100 times. Sample size was 10, and we assumed 80% would be the success rate here. Okay, you went to his game, so this was your p-hat, and you said 4 out of 10, which is 0.4, was his success rate that night. Okay, this is kind of funny. It's like, yeah, right, all right, man. Like, yeah, 80%, let's see. Goes to basketball game, gets out notepad, takes notes. Okay, so 0.4, there's a couple ways you could do this. If you literally even look at the distribution, it's not even happening. 0 dots out of 100 came up in the simulation. That's less than 5%, so that's an unusual occurrence. That makes me doubt him. He's probably lying. He's not going to be at an 80% throw. Another way of doing this is taking the mean and adding and subtracting 2 times the standard deviation, which takes a little bit of work. So if I do 0.8 minus 2 times 0.121, I get 0.558. Do the same thing, but add it. Whoopsies. Ugh. Come on. So, well, yeah, actually, yeah, 1.042. That is the middle 95. Technically, it went off the grid here. Right? Didn't make a mistake typing that. Yeah, no, that technically is it. Okay, so if you look for where 0.4 is, it's outside of our expected range of what a free throw thrower with an 80% rate would throw. So another way to think about this is if he truly was an 80% success rate thrower, it wouldn't shock me if he got in between these values on that night. Obviously, we'd have to cap this at 1.0. You can't make more than 100% of your shots. But the fact that he got out of that, for that to happen that one time, based on random chance alone, it's not very likely. So that causes me to doubt him. So I'd say I don't think he actually is an 80% free throw shooter. Whew. Lots of words. Okay, so again, if you want a more eloquent response, check out the answer key. All right, and similar problem, but phrased a little bit differently. We're going to do a coin one more time. You believe your friend has a weighted coin. One day you decide to test your theory by flipping the coin 20 times and recording the proportion of heads. Of the 20 coin flips, 14 ended up heads. So right now I'm thinking p hat equals 14 out of 20. To test this claim, he ran a simulation of 20 coin flips 200 times with the proportion of heads being 0.7. If I do 14 divided by 20, that is 0.7. So you ran the simulation now based on the sample. So this is different than the previous one. The previous coin flip question, we ran a simulation based on a fair coin. Right now we're running a simulation based on his coin. Okay, and we get this distribution. So keep in mind there's 200 dots here. Based on the results of the simulation, do you think the coin is unfair? Well, let's ask ourselves, if a coin was fair, wouldn't the proportion of heads be 0.5? So if I look on the graph, I'll zoom in here, just by counting dots, 0.5 or more extreme occurs 4 out of 200 times. So that's only 2% of the time. Another way of thinking about this is if you do our mean plus or minus 2 times the standard deviation and come up with that reasonable window. I bet you 0.5's outside of it. Oopsies. I typed that wrong. There we go. 0.5182. I just realized there's another number in here. I didn't mean to do that. Oh, come on. I'm really struggling with my online calculator today. Okay, 0.702 minus that, so 0.518. Change that to a plus 0.886. That doesn't actually belong there. Okay, so again, if you look for where 0.5, which would be a fair coin, flips or fits, 0.5 is outside the reasonable 95% interval that you came up with of that coin. So it's reasonable to expect that the proportion of heads on that coin would be between 0.518 and 0.886, but you're looking for where 0.5 is. That's not within the reasonable realm that you would predict, so therefore that tells me that in order for that to happen, it's not very likely. So this coin is likely weighted. Whew, alright. This was a mouthful. So hopefully this helps. This is your last unit test of the year, so make it a good one.